All right. Hi, so I'm Duke and so I'm from UT Austin. And today I'm gonna talk about my talk has the title on sums of practical numbers and polygonal numbers. And this talk is gonna be about the paper with the same title on sums of practical numbers and polygonal numbers, which I co-authored with Sai Teja Somu. And in this paper, we basically proved a few additive results involving practical numbers and polygonal numbers. And so basically they are about whether a natural number can or cannot be, be written as a sum involving practical numbers and polygonal numbers. And at the end, we also have two conjectures for future research, and one of them can be solved computationally. And so first, a brief introduction about practical numbers. So practical numbers were introduced by Srinivasan in 1948, and its definition is that practical numbers are natural numbers n such that every natural number less than or equal to n can be written as a sum of distinct positive divisors of n. And here are some examples. So I guess the first interesting example is 4, where 1 is 1 and 2 is 2 and 3 is 1 plus 2 and 4 is 4, and then 6 is another practical numbers. So all natural numbers less than or equal to 6 can be written as a sum of distinct positive divisors of 6. And you can see more information about practical numbers on this sequence on the Online Encyclopedia of Integer Sequences, the OEIS. If you're not familiar with this is a sort of like a repository for all sorts of sequences that is used to like basically store a lot of sequences, and it's really like common in the field of number theory and any fields that have number sequences in general. And then, well, I think this type of numbers are more familiar with. I'm just going through it to make sure. So polygonal numbers for integers s larger than or equal to 3, s-gonal numbers are the numbers of dots or circles that can be arranged in a regular s-gon. So for example, when s is 3, we have triangular numbers like in the picture. And then in general, we have the formula that the nth triangular number is n times n plus 1 over 2. And in general, for any s larger than or equal to 3, let us denote the nth s-gonal number by this ps of n. And we have this formula for the nth s-gonal number. And so just a brief overview over the previous additive results involving practical numbers. So in 1996, Murphy showed that every even natural number is a sum of two practical numbers. And so if you are familiar with the Goldbach conjecture, which which conjectures that every even natural number can be written as a sum of two prime numbers. And so this result, proven by Murphy, is basically the practical number version of the Goldbach conjecture. Although the prime version, the Goldbach conjecture, is still a conjecture, but an analog for practical numbers is already proven. And then in 2022, Pomerantz and Weingartner proved that every sufficiently large odd number can be written as a sum of a practical number and a prime. And then in 2023, Somu, Lee, and Kukla proved that all natural numbers congruent to 1 modulo 8 are expressible as a sum of a practical number and a square. And so now for our paper that we wrote basically this year, we have three main results. And the first is that every natural number can be written as a sum of a practical number and a triangular number. And for the second theorem, it is basically saying that all sufficiently large natural number can be written as a sum of a polygonal number of a practical number and two polygonal numbers. And so let S be a natural number greater than 3, then there exists a natural number ns, big N of S, such that all natural numbers greater than big N of S can be written as a sum of a practical number and two s-gonal numbers. And the third theorem has two parts. And the first part says that if S is 0 or 4 mod 12, then infinitely many natural numbers cannot be written as a sum of a practical number and an s-gonal number. And the purpose of this result is basically saying that in the second theorem, we need two s-gonal numbers. We need two polygonal numbers to cover all sufficiently large natural numbers. We cannot just use one polygonal number for all of the values of s. Although in the conjecture, we will conjecture that for certain values of s, we can actually cover all sufficiently large natural numbers with just one polygonal number. But I will get to the conjectures by the very end. And the second part of the third theorem is let E of S be the number of natural numbers that cannot be written as a sum of a practical number and two s-gonal numbers. Then we have that the limit as S approaches infinity of E to the S is infinity. The purpose of this result is showing that we cannot drop the all sufficiently large part of the second theorem because basically it is saying that the numbers that cannot be written as a sum of a practical number and two s-gonal numbers, it keeps increasing to infinity. And so we cannot we cannot we cannot have a stronger version of the second theorem that says that all natural numbers can be written as a sum of a practical number and two s-gonal number. We need all sufficiently large. We cannot make it stronger. Although again in the conjecture, we're going to conjecture that for a few values of s, we can have a stronger version that all natural numbers can be written as the sum of a practical number and two s-gonal numbers, but I will get to that later. And so first, a few lemmas for the first theorem. So the first lemma is that let m and n be natural numbers. Then there exists a natural number x between 1 and 2 to the n minus 1 such that x squared is congruent to 8n plus 1 modulo 2 to the n plus 2. And this lemma is from the 2023 paper by Somu and Kukla. And then the second lemma is that if m is a practical number and n is a natural number such that n is less than or equal to sigma of n plus 1, then m times n, the product m times n is a practical number. And this is from the paper by Morgenstern in 1991. And then this lemma is a rather important lemma, and we call that the characterization of practical numbers, which says that for any natural number n larger than or equal to 2 with this prime factorization, where the prime factors are ordered in the increasing order, then this natural number n is practical if and only if the first prime p sub 1 is 2, and then for the subsequent primes, we need the prime to be p sub j to be less than or equal to sigma of the products of the previous prime factors to their corresponding powers plus 1. And this sigma is the function that returns the sum of divisors of a natural number. And so this is the condition that basically characterizes all practical numbers. And a rather trivial corollary of this characterization of practical numbers is that all powers of 2 are practical numbers. Because the first prime is 2, and if we just don't have any other primes, then all powers of 2 are practical numbers. And another corollary from this is that the product of consecutive primes starting from 2 is practical number as well. So like P1, P2 is practical, P1, P2, P3 is practical. So that's why 6 and 30, 2 times 3 times 5, yeah, 30. 6 and 30 are practical numbers. And this was proven almost simultaneously by Stewart and Sierpinski in 1954 and 1955. And another lemma is that if x is an odd natural number, then x squared minus 1 over 8 is a triangular number. And the proof of this is basically just basic arithmetic. So if x is odd, then x is 2k plus 1 for some non-negative integer k. And we have that x squared minus 1 over 8 is equal to k times k plus 1 over 2. And so that is a triangular number. And so now let's get to the proof of the first theorem, which says that all natural numbers can be written as a sum of a practical number and a triangular number. And so first let n be a natural number and let m be the floor of the log base 2 of the square root of 8n plus 1. And the floor of a number, of a real number, is basically the largest natural number, the largest, no, not the largest natural number, but the largest integer, which in this case happens to be a natural number, that does not exceed the real number inside the floor bracket. And then, so by a previous lemma, there exists a natural number x such that x is between 1 and 2 to the m minus 1, and x squared is congruent to 8n plus 1 mod 2 to the m plus 2. And then since x is less than or equal to 2 to the m minus 1, and m is equal to the floor of log base 2 of square root of 8n plus 1, we have that x squared is less than 2 to the 2m, which is less than or equal to which is less than or equal to 8n plus 1. And then because x squared is less than 8n plus 1, and x squared is congruent to 8n plus 1 modulo 2 to the n plus 2, we have that 8n plus 1 minus x squared is equal to 2 to the n plus 2 times s for some natural number s. And that is because from the modular congruence, we have that it is equal to 2 to the n plus 1 times s for some integer s. But we know that x squared is less than 8n plus 1, and so we have that s must be positive, so it is a natural number, or at least non-negative. As m is equal to this floor of log base 2 of square root 8n plus 1, we have that 2 to the n plus 2 times s is less than or equal to 8n plus 1, which is less than or equal to 2 to the 2n plus 2. And this is just from the fact that m is the floor of this number here. So m is less than or equal to the thing inside, the log base 2 of square root of 8n plus 1, and n plus 1 is larger than this thing, this number, this real number inside. And so that's why we get this inequality here. And so this implies that s is less than or equal to 2 to the n. And then because 2 to the n minus 1 is practical number, so this is just the corollary from the characterization of practical numbers that I mentioned. All powers of 2 are practical numbers. And so 2 to the n minus 1 is a practical number. And s is less than or equal to 2 to the n, which is equal to sigma of 2 to the n minus 1 plus 1. And so by yet another lemma that we mentioned earlier, the product of 2 to the n minus 1 and s is a practical number. And then now, because x squared minus 1 is a triangular number, because x is an odd natural number. And we get that x is an odd natural number because of this congruence here, because it is 8n plus 1 modulo 2 to the n plus 2, which is an even number. So it's an odd mod, an even number, so that's odd. And then we have that 8n plus 1 minus x squared is equal to this 2 to the n plus 2 times s. And so just rearrange that and we get that n is equal to 2 to the n minus 1 times s plus x squared minus 1 over 8. And so we successfully wrote n, the natural number n, any natural number n, as a sum of a practical number and a triangular number. And so all natural numbers can be written as a sum of a practical number and a triangular number. And then now for the lemmas for the second theorem, the first lemma is that let p be an odd prime, let n be a natural number. Let s be a natural number greater than 3. Then there exist natural numbers x and y such that ps of x plus ps of y is congruent to n mod p. And so just to recall that the ps of x and the ps of y notation basically means the x s-gonal number and the y s-gonal number. So it's just the notation that we use for the polygonal number. And so the proof is if p divides s minus 2, then we have x equals n and y equals p satisfy the modular congruence. And this is a simple check. And if p does not divide s minus 2, then we have that the size of the set psi mod p for I between 1 and p is equal to the size of the set n minus ps of j mod p for j between 1 and p, which is equal to p plus 1 over 2. And this implies that these two sets must overlap. And so the intersection between these two sets is non-empty. Because for n minus psj mod p for j between 1 and p, and similarly for the set of psi mod p for I between 1 and p, half of half of the set must be at most p over 2. And so if the cardinality is p plus 1 over 2, that's larger than like the half threshold of the set. And so the intersection of these sets must be non-empty. And then so there exists, because the intersection of these two sets is not empty, there exist natural numbers x and y that produce the same uh produce the same congruency mod p, and so there exist natural numbers x and y such that ps of x plus ps of y is congruent to n mod p. And then another lemma is that let n be a natural number and s be a natural number greater than 3. Then there exist natural numbers x and y such that ps of x1 plus ps of y1 is congruent to n mod 2 for all natural numbers x1, which is congruent to x mod 4, and y1 congruent to y mod 4. And for the proof, it is just a check that if n is even, then when we let x equals 4 and y equals 4, it satisfies the condition, the equation. And if n is odd, then let x equals 4 and y equals 1, and it satisfies the equation. And another lemma, let p be a prime congruent to 1 mod 4. For all natural numbers n and k, there exist natural numbers x and y such that x squared plus y squared is congruent to n mod p to the k, and p does not divide y. And so by this rather like classical, I guess, result in modular congruence is that the size of the set of I square mod p for I between 1 and p, and the size of the set n minus j square mod p for j between 1 and p. These two numbers are both equal, and they are both equal to p plus 1 over 2. And so that means that this set intersect this set is not empty. They overlap. And so there exist natural numbers x and y that will give the same equivalence. Plus will give the same congruency in mod p in these sets. And so there exist natural numbers x and y such that x squared plus y squared is congruent to n mod p. And then the rest of the proof just follows from the Hensel's lemma and induction on the power k. Induction on the power k. And there are more details on the paper, but I'm not gonna go over the details of the induction here. And another lemma is that let S be a natural number greater than 3. There exists an odd prime p not dividing S minus 2 such that for all k and n in n, the set of natural numbers, there exists x, y, and n such that ps of x plus ps of y is congruent to n mod p to the k. And so let p a prime congruent to 1 modulo 4 such that p does not divide s minus 2. Then note that, so this is just from the formula of the polygonal number that I showed you in the very beginning, and just rearrange it. And then we have 8 times s minus 2 times ps of x is equal to this whole right hand side here. And because p is congruent to 1 mod 4 by the previous lemma, there exist natural numbers x naught and y naught such that x naught squared plus y naught squared is congruent to 8 times s minus 2 times n plus 2 times s minus 4 squared mod p to the k. Then let x and y be natural numbers satisfying these congruences. And just substitute these x and y into the equation of both. Oops, sorry. Right, so All right. So let x and y be natural numbers satisfying the congruences that satisfy this modulo congruence mod p to the k. Then we have that 8 times s minus 2 times ps of x plus 8 times s minus 2 times ps of y is, oh, no, not substitute into this, my bad. We substitute this x and y into this thing here. And so we get that this sum on the left-hand side is congruent to x naught squared plus y naught squared minus 2 times s minus 4 squared mod p to the k, which is 8 times s minus 2 and times 8 times s minus 2 times n mod p to the k. And because p does not divide s minus 2 and p is an odd prime, so p to the k, the GCD of p to the k and 8 times s minus 2 is 1. And so we have that pas of x plus ps of y is congruent to n mod p to the k. And a final lemma before getting to the proof of the second theorem. Let S be a natural number greater than 3, and let P sub I of S be the smallest prime for which the previous lemma hold. So let it be the smallest prime that such that this holds, such that it does not divide s minus 2 and there's this x and y such that ps of x plus ps of y is n mod p to the k. So P sub I of S is such smallest prime. Then there exists a real number A of S, such that for all x larger than or equal to 1, we have this inequality here. And to prove this, it's just a simple notice that the 2 times P sub S of 2 times P sub I of S times X. This is a quadratic polynomial. And so if we take this and divide it by x squared, then there is a real number that bounds that this expression above for all x larger than or equal to 1. And then, so now let's get to the proof of the second theorem, which is the theorem that states that all sufficiently large natural numbers are expressible as a sum of a practical number and two polygonal numbers. So let Pi denote the ith prime, and let P sub I of S be the prime as defined in the last lemma. So it is this same thing here. And then so by the previous lemma, there exists a real number A of S such that 2 times Ps of 2 times P sub I of S times x divided by x squared is less than or equal to A of S for all real numbers x larger than or equal to 1. Then let R be the smallest natural number such that R is larger than or equal to I of S, and sigma of P1 times P2 times up to P sub R divided by P1 times P2 dot up to P sub R is larger than or equal to A of S. And such an R is well defined because we know it has been shown that the product over prime P of 1 plus 1 over P diverges. And so what that means is that, so this product of, so this expression on the left-hand side here is the finite version, the truncated version of this product over prime P. This is the product from the first prime to the nth prime of 1 plus 1 over P. And if this product here diverges, then that means the expression on the left-hand side will grows indefinitely, and so there must be some R at which this expression exceeds any real number because this infinite product here diverges. And then let n of s be this expression right here, 2 times p of ps of 2 times p1 p2 up to pr, and consider any natural number n greater than ns. So this is gonna be like the lower bound of the numbers that can be written as a sum of a practical number and two polygonal numbers. Let k be the largest natural number such that 2 times ps of this expression is less than n. So it is, so the thing inside the ps is 2 times p1 plus p2 up to pr, except that the p sub I of s, this is like the special prime with the special condition that we defined in the previous lemma. This prime is raised to the kth power. And so k is the largest natural number such that this expression is less than n. And so let nk be the thing inside the bracket here. So 2 times p1 times p2 up to pr with p sub is raised to the k power. Then from the definition, we have that 2 times ps of nk we defined here, is less than n, which is less than or equal to 2 times ps of p sub is times nk. The reason why is because if we multiply p sub is to the nk here, then this p sub is will be raised to the k plus 1 power. And k is the largest number such that this expression is less than n. So if we raise the power of p sub is to just 1 larger, then it's gonna not be less than n anymore, and it's gonna be larger than or equal to n. So this is just based on how we define the number k. Then, by a previous lemma, there exists a solution to this equation here. Ps of x plus ps of y is congruent to n mod pi for all I between 2 and r, and for I that is not equal to I of s. And then by another lemma, we have that there exists a solution x mod 2p1 and y mod 2p1, which is just mod 4 because p1 is the first prime, which is 2, and 2 times 2 is 4. To the equation, ps of x plus ps of y is congruent to n mod p sub 1, which is just mod 2. And then so by another lemma, again, there exists a solution x mod p sub I of s to the k and y mod p sub I of s to the k to this equation. And then by the Chinese remainder theorem, there exists solution x mod nk and y mod nk to this equation here. Oops. Yeah. And so there exists a solution to this equation by Chinese remainder theorem. And so there exist unique natural numbers x, y larger than or less than or equal to nk, such that ps of x plus ps of y is congruent to n mod nk over 2. And then this, together with the fact that n is larger than 2 times ps of nk, this is just from the definition of the number k that we defined earlier. This will imply that 2 times n minus ps of x minus ps of y divided by nk is a natural number. The reason why is because we know that n minus this whole thing will be a multiple of nk over 2. So n minus ps of x minus ps of y divided by nk over 2, which is times 2 over nk, will be an integer. And furthermore, we know that n is larger than this thing. So n minus ps of x minus ps of y must be positive, and so it must be a natural number as well. And then so we note that 2 times n minus ps of x minus ps of y over nk is less than or equal to 2n over nk, and this is less than or equal to 4 times ps of p sub is times nk over nk. And then from the last lemma, just let x equal nk over 2. Then we have this thing here. And then so 2 times n minus ps of x minus ps of y over nk is less than or equal to 4 times ps of p sub I of s times nk over nk, which is less than or equal to a of s times nk over 2. And then because as times nk over 2 is less than or equal to sigma of nk over 2. And this is just because of how we defined this is because of this part right here. And so because of that, oh no, it's because of the thing below, my bad. So we have as times nk over 2 is less than or equal to sigma of nk over 2 because we have this expression right here. Well, it was also partly because of the part that I went back earlier to, because of how we defined the number R here. And so we have 2 times n minus ps of x minus ps of y over nk is less than or equal to as times nk over 2, which is less than or equal to sigma of nk over 2. And so note that this whole number here is a practical number by the characterization of practical numbers. And then by the previous lemma on the product of two numbers being practical number, then we have that, so this thing is less than or equal to the sigma of this thing, which is obviously less than sigma of this plus 1. And we know that this nk over 2 is a practical number. And so this thing times the nk over 2, which is n minus ps of x minus ps of y, is a practical number. Because this is practical, and this thing is less than the sigma of this number plus 1. And so because this is a practical number, then so we have that n minus two polygonal numbers is a practical number. And so we successfully wrote n as a sum of two polygonal numbers and a practical number. And so all sufficiently large natural numbers can be written as a sum of a practical number and two polygonal numbers. And then for the third theorem, we need one more lemma, which says that if q is a practical number such that q is neither divisible by 3 nor by 4, then q is 1 or 2. And so this is going to be proved by contradiction. So for the sake of contradiction, assume that q is larger than 2. And then because q is larger than 2 and 4 does not divide q, the natural number q should have at least one odd prime divisor. And just to recall from the characterization of practical numbers, the first prime factor should always be 2. But then 4 does not divide q, and so 2 cannot be raised to any higher power. It's just 2. And then it must have another odd prime divisor as well, because q is larger than 2. Then let p be the smallest odd prime divisor of q. Because 3 does not have a q, we further have that p must be at least 5. Because p is larger than or equal to 5, which is larger than sigma of 2 plus 1, then by the characterization of practical numbers, we can conclude that q is not practical. Because if we want 2p or 2 times p to any power to be a practical number, we need p to be less than or equal to sigma of 2 plus 1. But here we have larger, and so q is not practical number. And so that is a contradiction. And so q cannot be larger than 2. Q must be smaller than or equal to 2, and practical numbers that are smaller than or equal to 2 are just 1 and 2. And so for the proof of part A of the third theorem, which says that if S is 0 or 4 mod 12, then infinitely many natural numbers cannot be written as a sum of a practical number and an s-gonal number for those particular values of S. So first note that Ps of n is equal to a times n squared plus b times n, where a and b are these values. And this is just straight from the formula for the nth s-gonal number. And if s is 0 or 4 mod 12, then a is odd and it's not divisible by 3, and b is even. And so just some algebraic rearrangement, we can rewrite this expression right here as this thing right here. Ps of n is equal to 1 over a times an plus b over 2 squared minus b squared over 4 for all non-negative integers. And because 2 is a quadratic non-residue modulo 3 and 4, we have that Ps of n is never congruent to a inverse times 2 minus b squared over 4 mod 3 and mod 4. And so first of all, we can write A inverse here because A has inverse mod 3 and mod 4 because we know that A is odd. So A has inverse mod 4 and A is not divisible by 3. So we have A inverse mod 3. And it is never congruent to this is because here we have a square, but 2 is not a quadratic residue mod 4 and mod 3. And so it's never congruent to this thing right here. No polygonal number is gonna be congruent to this value mod 3 mod 4 for the values of s that we're considering here. And so let R be a natural number such that R is congruent to this number. It's the same number here. And let X be any positive real number. Then let K be a natural number congruent to R modulo 12 and not exceeding X such that K is equal to PS of M plus Q. So K is a sum of a polygonal number, an s-gonal number, and a practical number. So for some M, non-negative, and for some practical number Q. And so K is particularly R mod 12. And because K is R mod 12, we have the 3 and 4 do not divide K minus PS of M because we already showed that no polygonal number, no s-gonal number is gonna be congruent to R mod 12 for the values of S that we are considering here. And K is R mod 12, so the difference between K and these s-gonal numbers are never gonna be 0 mod 12. They're never gonna be 0 mod 3 and 0 mod 4, and so 3 and 4 do not divide this. And then by the previous lemma, we know that K minus PS of M is a practical number, and 3 and 4 do not divide that practical number. And so K minus PS of M must be 1 or 2. So K is in the sets PS of N plus 1 for N non-negative and PS of N plus 1 less than or equal to X because K is less than or equal to X. We have defined it here. Union PS of N plus 2 where union the set containing PS of N plus 2 where N is non-negative integer and PS of N plus 2 is less than or equal to X. And so this is basically just saying that if we write K as a sum of a polygon of an s-gonal number and a practical number Q, that Q can only be either 1 or 2. So it's either in this set or this set. And then because we know that the cardinality of these two sets is O is to the order of O of square root of X, we have that there are at most O of square root of X natural numbers not exceeding X that are congruent to R modulo 12 and expressible as a sum of a practical number and an s-gonal number. Then because they are x over 12 plus O1 natural numbers not exceeding x that are congruent to R mod 12, there are at least this many x over 12 plus O of square root of x natural numbers not exceeding x that are congruent to R mod 12 and not expressible as a sum of a practical number and an s-gonal number. And this proves the result because as we take x to approach infinity, as we let x approach infinity, this will explode to infinity. And so there are infinitely many numbers congruent to R mod 12 that are not expressible as a sum of a practical number and an s-gonal number. And if there are infinitely many numbers that are congruent to R mod 12 that are not expressible as a sum, then, well, there are infinitely many natural numbers that are not expressible as a sum of a practical number and an s-gonal number for S that are congruent to 0 and for mod 12. And then moving on to the part B of the third theorem, which says that the number of natural number.
For the previous slide, why was the cardinality of those sets O of square root of x?
Well, because these PS of n, the formula for them is, hold on. Yeah, because basically the intuition is that these formulas for the polygonal numbers, they are a quadratic formula. They are of they are of the form of like some number times n squared plus some number times n. And so for all for all of those like quadratic forms less than or equal to x, then sort of like these n must be like roughly less than or equal to the square root of x, because like if like sometimes a number times n squared is less than or equal to x, then that n must be roughly less than or equal to some number times square root of x, and so it is of the order of square root of x.
I see. Thank you.
Yeah. And so moving on to part B. So part B says that the number of natural numbers that cannot be written as a sum of a polygonal number and two s-gonal numbers is going to increase to infinity as we let s approach infinity. And so the approach is that we count the natural numbers less than s that can be represented as a sum of a practical number and two s-gonal numbers. And so we would need to take the s-gonal numbers that are less than s. And the s-gonal numbers that are less than s are only 0 and 1. And so if n less than s is the sum of a practical number and two s-gonal numbers, then n is in the set of p plus I, where p is a practical number, p is less than or equal to s, and I is either 0 or 1 or 2. Because the s-gonal numbers are less than s are only 0 and 1, so we can only have, so the sum of two s-gonal numbers is gonna can only be plus 0, which is 0, or plus 0 plus 1, which is 1, or plus 1 plus 1, which is 2. And then from a result in the 2015 paper by Vin Gardner, it follows that the cardinality of this set here is to the order of s over log of s. And so the result here that we're using is basically saying that the number of practical numbers not exceeding x is asymptotically equivalent to a constant times x over log x. And so if you are familiar with the prime number theorem, the result proven by Vin Gardner that we are using here is basically the practical version, the practical number version, the practical number analog of the prime number theorem. It just says that the number of practical numbers less than or equal to x is asymptotically equivalent to a constant times x over log x. So it's to the order of x over log x, or here we use s. And so because of that, the numbers of natural numbers less than s that can be written as the sum of a practical number and two s-gonal numbers is this many. And so there are at least s minus this, or it's the same thing as s plus this, s plus o of s over log x, log s numbers less than s that cannot be written as a sum of a practical number and two s-gonal numbers. And this proves the result because, well, as we take s to be approaching infinity, then this thing is close to infinity. And so the number of natural numbers that cannot be written as a sum of a practical number and two s-gonal numbers will approach infinity as s approaches infinity. And so just a brief revisiting to the main results. So first, we have that all natural numbers can be written as a sum of a practical number and a triangular number. And then for s larger than 3, we proved that there exists a big N of s such that all natural numbers larger than this number right here can be written as a sum of a practical number and two s-gonal numbers. So basically, all sufficiently large natural numbers can be written as a sum of a practical number and two s-gonal numbers for s larger than 3. And then the third result, first part, for s that are congruent to 0 or 4 mod 12, there are infinitely many natural numbers that cannot be written as a sum of a practical number and an s-gonal number. And that partially justifies why we need two s-gonal numbers in the second theorem. Although, because in the part A here, we only prove this to be the case for s that are 0 or 4 mod 12. So the first conjecture is that if s is larger than 3, because we already proved in the case of s equal 3 that all natural numbers can be written as a sum of a practical number and a triangular number. And for s that are not 0 mod 12 and not 4 mod 12, then all sufficiently large natural numbers can be written as a sum of a practical number and one s-gonal number instead of two. And so this is our first conjecture in the paper. And these are just a bunch of OEIS sequences that, well, I uploaded on OEIS related to this conjecture, which contains the data related to this conjecture. And so in the paper, if you read the paper, there's gonna be a table of the values of the numbers that we calculated, like the number of natural numbers less than 10 to the 8, 10 to the 8th power, and the largest number less than 10 to the 8th power that cannot be written as a sum of a practical number and an s-gonal number for different values of s. And we have that data to, like, computationally, they justifies this conjecture. And these sequences will contain pretty much similar data, but like a little bit more in details, a little bit in more details. And getting to part B, revisiting the part B of a third result, it basically says that the number of natural numbers that cannot be written as a sum of a practical number and two s-gonal numbers will increase to infinity as s approaches infinity. And that partially justifies why we need this lower bound, n of s, and all natural numbers larger than n of s will be able to be written as a sum of a practical number and two s-gonal numbers. But we cannot remove the all sufficiently large part of the second theorem for all values of s. We cannot have a stronger version that, like, say, for all s larger than 3, all natural numbers can be written as a sum of a practical number and two s-gonal numbers. We cannot have that stronger version of theorem 2 of the second theorem here. Although for our second conjecture, and for this conjecture also, we also checked it computationally, that for s in 4, 5, 6, 7, 8, 10, all natural numbers can be written as a sum of a practical number and two s-gonal numbers. And this is our second conjecture. And these are the OEIS sequences related to this conjecture containing some detailed data and stuff like that. And so this second conjecture, if you can find a way to write a code that is algorithmically more optimal, or if you have like some huge computational power, then you can check this conjecture completely computationally. Although, of course, the theoretical way would be more interesting, but I mean, a computational way would be good as well. But uh, so I checked these two conjectures by a Python code, which is also cited in the paper. And I mean, to be honest, I'm not really good at Python, and so the codes I wrote, like for checking up to like 10 to 8, it could take like a day. And so, and for this second conjecture, although in our second theorem, we already have a lower bound on the numbers that can be written as a sum of a practical number and two s-gonal numbers. And so if you want to check the second conjecture computationally, you just need to calculate, well, just need to calculate this value n of s here, and then check all numbers below n of s to make sure that all numbers below n of s are expressible as a sum of a practical number and two s-gonal numbers as well. And that would verify the second conjecture. That would, well, prove the second conjecture. But the thing is, this n of s is going to be very large. And I do not know the exact value or like a good estimate, but I know for sure that it is larger than 10 to the 8th, because I sort of like checked for these conjectures by checking up to 10 to 8th, and that is not enough to like prove the conjecture. That's just like to get a sense that this conjecture should be true. And so yeah, that's it for the talk. And if you want to read the paper for more details and for more information, more data on the conjectures and stuff like that, scan the QR code here to read our paper here. That's it. Thank you for listening.
Thank you, Drew.
So are there any additional questions, anything like that?
Yes, are there any questions? Wait, I have a question. So like you said that there was like a prime number theorem thing for the practical numbers. So is there like any a general relationship between practical numbers and prime numbers?
Well, there's not really any general like relationship between the two. It's just that the two have pretty much many sort of like analogous results. Like how hold on, I'm gonna share again. So I mean, oops, wait, there's something wrong here. Oh, yeah. Oh, wait. So the thing you're talking about is this. So yeah, so the result we're using here says that all practical numbers less than or equal to x is asymptotically equivalent to a constant times x over log of x. And that is basically the practical number analog version of the prime number theorem, because the prime number theorem says that all prime numbers less than or equal to x is asymptotically equivalent to x over log of x. And I mean, this is, I don't know, I did not read this paper in detail, but so I don't really know if they actually use anything like related to the proof of the prime number theorem there, or like similar or have some connection to the prime number theorem. But it's, I mean, it's just like sort of like a coincidental analog. And another interesting analog that I mentioned like way in the beginning between practical numbers and prime numbers is that, so it has been proved that every even natural number is a sum of two practical numbers. And if you're familiar with like the prime number stuff, there's the Goldbach conjecture, which conjectures that every even natural number is a sum of two prime numbers. And this is still a conjecture, but there is a practical number analog to that, which is already proven right here that every even natural number is a sum of two practical numbers. And I mean that's just like a sort of like a coincidental analog, I think. And another interesting thing is that, so like in prime numbers, there's a conjecture that there are infinitely many twin prime numbers, which is that there are infinitely many prime numbers p such that p plus 2 is also a prime number. And I think, I'm not very sure, but I think it is proven, or at least conjectured. I'm definitely 100% sure that it is conjectured, but I think it is also proven that there are infinitely many twin practical numbers, which are the practical numbers q such that q plus 2 is also a practical number. I think that is proven. I am sure it has been conjectured, but I'm not very sure if it is proven or not, but I'm like 90% sure it is proven. Yeah, so there are just like a lot of like analogs, analogous results between, or like between the results in of practical numbers and conjectures, or like of prime numbers, or between two results of practical numbers and prime numbers. And I mean, it's just some interesting coincidental analogs. It's not really like practical numbers have really tight connection to primes or things like that.
Hmm, interesting. Yes. Um, okay, I guess if there are no more questions, then um we can finish. Thank you very much, Duke, for coming
Thank
to give
you.
a talk
Bye.
for us.